Voyager 1 is dying. Right now, roughly 25.8 billion kilometers from Earth, a machine the size of a small car is flying through absolute darkness at 61,000 kilometers per hour. It has 2 functioning instruments left. It lost another one 3 weeks ago. Its power supply drops by 4 watts every year, and the engineers at the Jet Propulsion Laboratory in Pasadena, California, are running out of things to shut off. In November of this year, Voyager 1 will cross a distance that has a name, 1 light day. The point at which a signal from Earth, traveling at the fastest speed the universe allows, takes 24 hours to arrive. If an engineer sends a command on Monday morning, the spacecraft will not respond until Wednesday. If something goes wrong out there tonight, nobody on Earth will know until tomorrow night, and by then, it may already be too late to fix. Voyager 1 has been flying for 49 years. It was designed to last 5. It has crossed boundaries that no model predicted correctly. It has detected sounds in interstellar space that no theory can fully explain. And it is carrying a golden record containing the sounds of life on Earth, music, greetings in 55 languages, the cry of a newborn child, all of it hurtling through a region of space where there is nothing alive to hear it. This is not a story about a spacecraft. This is a story about what happens when you throw a message into the void and the void answers with something you did not expect. And the part that nobody is talking about is what Voyager found at the farthest place humanity has ever reached and why the data it sent back broke 3 predictions at the same time. September 5th, 1977, Cape Canaveral, Florida. A Titan IIIe rocket punched through the atmosphere, carrying 825 kilograms of instruments, antennas, and a nuclear battery. Voyager 1 was not alone. Its twin, Voyager 2, had launched 16 days earlier. The 2 spacecraft were built for a window that would not open again for 175 years. Jupiter, Saturn, Uranus, and Neptune were drifting into an alignment so rare that the engineers who first noticed it in the late 1960s called it the Grand Tour. A spacecraft launched at the right moment could use each planet's gravity as a slingshot, bending its trajectory and accelerating without burning fuel. NASA originally planned an ambitious mission to visit all 4 outer planets. Budget cuts killed that idea. The program was scaled back to just Jupiter and Saturn, and the name was changed from Mariner Jupiter-Saturn to Voyager. The probes were designed to operate for 5 years. After that, nobody expected them to matter. But here is the part that the timeline does not capture. The engineers who built Voyager knew something they could not prove. They suspected the spacecraft might survive longer than the budget allowed them to plan for. So they made decisions that would only matter decades later. They used redundant computer systems. They installed backup thrusters. They placed a golden record on each probe, a 1-2-inch gold-plated copper disc containing 115 images, greetings in 55 languages, 90 minutes of music from Bach to Chuck Berry, and natural sounds, wind, thunder, birdsong, whales. The record was curated by a committee chaired by Carl Sagan. It was designed to survive for 1 billion years in the vacuum of space. The spacecraft carrying it was designed to last 5. That contradiction tells you everything about what Voyager really was. Not a mission, a bet. A bet that something built by human hands could outlast the civilization that built it. Voyager 1 reached Jupiter in March 1979. What it found there was not what the textbooks predicted. The first surprise was Io. Jupiter's innermost large moon was supposed to be a frozen, cratered world. Instead, Voyager caught it mid-eruption. Active volcanoes, blasting sulfur hundreds of kilometers above the surface. It was the first time volcanic activity had been observed anywhere beyond Earth. The discovery happened almost by accident. Linda Morabito, a navigation engineer at JPL, was processing an image of Io taken for trajectory calibration, not science, when she noticed a strange crescent-shaped plume on the limb of the moon. She thought it was another moon behind Io. It was not. It was a volcanic eruption caught in profile, visible only because Voyager happened to be at the right angle at the right moment. Nobody had predicted volcanoes on Io. The tidal forces from Jupiter's gravity, flexing the moon's interior like a stress ball, had not been seriously modeled as a heat source. Voyager forced the models to be rewritten overnight. Stan Peele, a physicist at UC Santa Barbara, had actually published a paper predicting tidal heating just days before the Voyager flyby. Almost nobody had read it. When the images came back, Peele's paper went from obscure to foundational in a week. Science works like that sometimes. The right idea, sitting in a journal, invisible, until a machine 600 million kilometers away sends back a photograph that makes the idea undeniable. Jupiter also gave Voyager something else: speed. The gravity assist from the flyby accelerated the spacecraft by roughly 16 kilometers per second without burning a single gram of fuel. The planet's mass bent Voyager's trajectory and flung it towards Saturn faster than any rocket engine could have managed. The spacecraft was borrowing velocity from the planets themselves, trading momentum from objects that would not notice the loss. Jupiter barely twitched. Voyager gained years. Then came Saturn. In November 1980, Voyager revealed the rings in a detail no telescope had achieved. They were not the smooth, solid bands they appeared to be from Earth. They were thousands of individual ringlets, braided and kinked by the gravitational influence of small moons embedded within them. Shepherd moons, they were called. Tiny objects whose gravity sculpted the ring edges into sharp boundaries that should not have existed. The rings themselves were made of ice and rock, particles ranging from grains of sand to the size of houses, all orbiting Saturn at different speeds in a disk so thin relative to its width that if you scaled it down to the size of a football field, it would be thinner than a razor blade. But the real decision at Saturn was not about the rings, it was about Titan. Saturn's largest moon had a thick, opaque atmosphere, the only moon in the solar system with one. NASA had a choice. They could redirect Voyager 1 to fly close to Titan and study its atmosphere, but the trajectory required to do that would fling the spacecraft upward, out of the plane of the solar system, ending any chance of visiting Uranus or Neptune. Or they could skip Titan and continue the grand tour. They chose Titan. The decision meant Voyager 1 would never see another planet. It would fly upward, away from every world in the solar system, into the dark, and it would keep going. For the next 32 years, Voyager 1 flew through what scientists call the heliosphere. This is the bubble. The sun does not just emit light. It blows a continuous wind of charged particles outward in every direction, a supersonic stream of plasma moving at 400 kilometers per second. This wind inflates a bubble around the solar system, pushing against the gas and dust of interstellar space. Inside the bubble, you are under the sun's influence. The magnetic field you measure belongs to the sun. The particles hitting your instruments come from the sun. Outside the bubble, everything changes. The magnetic field belongs to the galaxy. The particles come from exploded stars, from cosmic events millions of years old. The boundary between these two environments has a name: the heliopause. And for decades, physicists had built models predicting exactly what would happen when a spacecraft crossed it. 3 things were supposed to occur simultaneously. Solar wind particles should drop to 0. Galactic cosmic rays should spike, and the magnetic field should rotate sharply, changing from the sun's orientation to the galaxy's orientation. Clean, predictable, like crossing a wall from one room into another. On August 25, 2012, Voyager 1 crossed the heliopause at a distance of roughly 122 astronomical units from the Sun, about 18.2 billion kilometers. The solar wind particles dropped. The cosmic rays spiked, but the magnetic field refused to rotate. It stayed, pointing in roughly the same direction it had been inside the heliosphere. That was not supposed to happen. 3 separate things were predicted. 2 of them occurred exactly as expected. The third, the one that should have been the clearest signal that Voyager had entered a new environment, did not behave the way any model said it would. The physics community spent years arguing about what this meant. Some researchers at the time questioned whether Voyager had actually left the heliosphere at all. The plasma wave instrument, run by Don Gurnett at the University of Iowa, eventually settled the debate by detecting plasma oscillations at a density consistent with the interstellar medium. roughly 40 times denser than the plasma inside the heliosphere. Voyager was outside. The magnetic field was simply not cooperating with the models. Nobody has fully explained why. The leading hypotheses involve complex interactions at the boundary, where solar and galactic magnetic fields may be more entangled than the clean separation models assumed. But as of today, the magnetic field direction at the heliopause remains one of the open problems in heliophysics. Not because the data is bad, because the models were too simple. And then the hum started. In 2017, Voyager 1's plasma wave instrument began detecting something that had not been there before. A faint, persistent, narrowband signal in the plasma surrounding the spacecraft. Not the sharp bursts of plasma oscillations that had been triggered by solar shockwaves in previous years. Those were loud, brief, and explained. This was different. A continuous low-level vibration in the interstellar plasma, humming at a nearly constant frequency, week after week, month after month. Stella Koch-Ocker, a doctoral researcher at Cornell University, led the analysis. Her team published the finding in Nature Astronomy in 2021. The signal had been present, at detectable levels, for almost 3 years straight, over a distance of roughly 10 astronomical units. It was faint enough that it required averaging multiple observations to pull it out of the noise, but it was persistent and narrowband, which ruled out random instrument artifacts. The frequency of the hum corresponds to the local plasma density, essentially the number of charged particles per cubic centimeter in the interstellar gas. What the hum revealed was that the interstellar medium is not smooth. It has structure, small-scale density fluctuations, tracing turbulence in the gas between the stars. This turbulence had been predicted theoretically, but never directly measured at this resolution. Voyager was hearing the weather report of interstellar space. But the mechanism producing the hum itself is not settled. 2 candidates have been proposed. One is thermally excited plasma oscillations, essentially the random thermal motion of electrons in the gas generating faint waves at the plasma frequency. The other is quasi-thermal noise, a related but distinct process in which the spacecraft's antenna passively picks up fluctuations in the electric field caused by the surrounding plasma. Both mechanisms are physically plausible. Neither has been confirmed. The distinction matters because it affects how we interpret the density measurements and what they tell us about the structure of the interstellar medium at scales we have never sampled before. What makes this significant is not the hum itself. It is the fact that Voyager is the only instrument we have at that location. There is no second probe to cross-check the data. There is no ground-based telescope that can replicate the measurement. And the instrument detecting the hum, the plasma wave subsystem, is one of only 2 instruments still functioning on the spacecraft. As of the 17th of April, 2026, it is down to 2, the magnetometer and the plasma wave system. Everything else has been shut off to conserve power. The power situation is the thing that gives this story its clock. Voyager 1 runs on a radioisotope thermoelectric generator, 3 slugs of plutonium, 238, decaying steadily, converting heat into electricity through thermocouples. At launch, the RTG produced about 470 watts. By 2026, it produces somewhere around 220 watts. That is less than a household light bulb, and it loses another 4 watts every year. The spacecraft needs a minimum amount of power to keep its systems warm enough to function. In the cold of interstellar space, ambient temperature sits at roughly 3 degrees above absolute zero. If the fuel lines freeze, the thrusters fail. If the thrusters fail, the antenna drifts. If the antenna drifts by more than 2 degrees, the signal disappears. Every component on Voyager 1 is now single string. No backups. No redundancy. Some thruster lines are already clogged with hydrazine residue. The engineers have been shutting down systems one by one for years, in an order that was agreed upon long ago by the science and engineering teams together. On April 17th of this year, they sent the command to shut off the low-energy charged particles experiment. The LECP had been running almost continuously for 49 years. It measured ions, electrons, and cosmic rays from both the Sun and the galaxy. It provided critical data about the structure of interstellar space, detecting pressure fronts and regions of varying particle density beyond the heliosphere. Shutting it off was not an emergency decision. It was a planned sacrifice. On February 27th, during a routine roll maneuver, Voyager 1's power levels dropped unexpectedly. The engineers knew that any further unplanned drop could trigger the spacecraft's automatic fault protection system, which would start shutting things down on its own in an order that might not be recoverable. So they acted first. The command took 23 hours to reach the spacecraft. The shutdown procedure took another 3 hours and 15 minutes. One small component of the LECP, a motor that spins the sensor to scan in all directions, was left running. Everything else went dark. There is one move left. The engineers call it the Big Bang, a coordinated swap of several powered systems all at once, trading older components for lower power alternatives. The idea is to keep Voyager warm enough to operate while drawing less electricity from the failing RTG. They will test it on Voyager 2 first, in May and June of this year, because Voyager 2 has slightly more power and is closer to Earth, making it a lower risk candidate. If it works, they will attempt the same procedure on Voyager 1 no sooner than July. If the Big Bang succeeds, there is even a chance, a slim one, that the LECP could be switched back on. If it fails, or if another unexpected power drop occurs before they can attempt it, the end comes faster. The engineers believe they can keep at least one instrument running on each spacecraft into the 2030s. The RTGs may produce enough power for engineering telemetry, basic location and status data until approximately 2036. After that, both probes go silent. They will still be flying. At 61,000 kilometers per hour, Voyager 1 will continue moving through interstellar space for tens of thousands of years, but nobody will know where it is. Nobody will hear what it detects. The hum will continue, and no one on Earth will be listening. Consider what Voyager has actually measured in interstellar space, not what the press releases emphasize, what the instruments recorded. The plasma density outside the heliopause is not uniform. It fluctuates. The interstellar medium has structure at scales of astronomical units, density waves, and turbulence that trace energy cascading down from larger astrophysical processes, supernova remnants, stellar winds from nearby stars, the large-scale flow of the local interstellar cloud through which our solar system is currently moving. Voyager's plasma wave data, sampled at intervals of roughly 0.03 AU, is the highest resolution map of interstellar plasma density ever created. Nothing else comes close. No other instrument, on Earth or in space, can make this measurement. The magnetic field in interstellar space, measured by the magnetometer, is roughly 0.4 to 0.5 nanotesla, about 100,000 times weaker than the field at the surface of Earth. It is tilted at an angle that does not match what models predicted, based on observations of distant pulsars and the large-scale galactic field. This discrepancy is another open problem. The local interstellar magnetic field may be distorted by the heliosphere itself, the Sun's bubble pressing against it and warping the field lines in its immediate vicinity. But we cannot confirm that from one probe at one location. We would need a second measurement at a different point to separate local distortion from large-scale structure. There is no second measurement. There never will be unless a new interstellar probe is launched. The most serious proposal, the Interstellar Probe Study, led by Johns Hopkins Applied Physics Laboratory, envisions a spacecraft that could reach 1,000 AU from the Sun within 50 years, using a close solar gravity assist and advanced propulsion. Even in the most optimistic timeline, such a mission would not launch before the mid-2030s and would not reach interstellar space until the 2080s. By then, Voyager will have been silent for half a century. And then there is the golden record. Each Voyager carries one, a phonograph record made of gold-plated copper, enclosed in an aluminum cover, electroplated with uranium. 238. The uranium serves as a clock. Any civilization that finds the record can measure the remaining uranium and calculate how long it has been traveling. The record contains 115 images encoded as analog waveforms. Photographs of Earth, human anatomy, mathematical definitions, the structure of DNA. It contains greetings in 55 human languages, including Sumerian, which has not been spoken in over 4,000 years. It contains audio, the sound of rain, surf, wind, thunder, birds, whales, a mother kissing her child. Music by Bach, Mozart, Beethoven, Stravinsky, Chuck Berry, Blind Willie Johnson. The committee that selected the contents included Carl Sagan, Anne Druyan, Frank Drake, and others. Druyan later described the recording sessions as one of the most emotionally intense experiences of her life. The record was designed to last 1 billion years in the vacuum of space. Here is the part that does not get said enough. Nobody will ever play it. The probability that either Voyager will encounter another civilization or even another star system within the operational lifetime of the record is effectively zero. Voyager 1 will pass within 1.6 light-years of the star Gliese, 445 inches, the constellation Camelopardalis, in roughly 40,000 years. It will not enter that star's planetary system. It will drift past, in silence, carrying a message from a species that may no longer exist. On February 14th, 1990, as Voyager 1 was already 6 billion kilometers from Earth and heading outward with its planetary mission complete, Carl Sagan convinced NASA to turn the camera around, point it back toward home. The resulting photograph showed Earth as a fraction of a single pixel, suspended in a scattered beam of sunlight. Sagan called it the pale blue dot. He wrote about it with a kind of clarity that landed harder than most scientific papers. He described everyone you have ever heard of, every human being who ever lived, every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher of morals, every saint and sinner in the history of our species, living their lives on a mote of dust suspended in a sunbeam. The photograph worked because of the black background. The emptiness made the dot meaningful. The isolation made the message land. But the black background was not empty. It was full. Full of interstellar plasma, full of magnetic fields, full of a hum that would not be detected for another 27 years. Voyager just did not have the instruments pointed in the right direction to see it. The loneliness we read into that image was ours, not the universe's. The universe was busy. We were the ones projecting silence onto a cosmos that was vibrating at frequencies we had not yet learned to hear. The record was never really meant for aliens. It was meant for us. It was a way of saying, this is what we are. This is what we sound like. This is what we care about enough to send into the dark, knowing it will never be heard. The act of sending it was the message. And now, the machine carrying that message is losing power, one instrument at a time, one system at a time. In a few months, engineers in Pasadena will attempt a procedure they have never tried before on a spacecraft that is 49 years old, 25.8 billion kilometers away. Running on the heat of decaying plutonium with no backup systems and no way to physically repair anything that breaks. If the Big Bang works, Voyager lives a little longer. If it does not, the timeline accelerates. The last data Voyager sends will probably not be science. It will be engineering telemetry, temperature readings, power levels, the equivalent of a pulse check. The spacecraft will report its vital signs until the generator can no longer sustain the transmitter. Then, the carrier signal will drop below the detection threshold of the Deep Space Network's 70-meter antenna in Canberra, Australia, the only dish on Earth powerful enough to hear it. And Voyager will cross a second boundary, not the heliopause, the boundary between communication and silence. It will still be out there, moving at 17 kilometers per second through the local interstellar cloud, a warm, diffuse region of partially ionized gas, roughly 30 light-years across, that our solar system entered sometime in the last few thousand years. Eventually, tens of thousands of years from now, it will leave the local cloud and enter the next region of interstellar space. Whatever that looks like, we will not know, we will never know. Voyager 1 is the farthest object humanity has ever placed into the universe. It is also the loneliest. It has no companion. Voyager 2 is 4.5 billion kilometers behind it, heading in a different direction. No other spacecraft will reach Voyager 1's current distance for decades. It is measuring a region of space that no other instrument can access, reporting data that no other source can verify, transmitting findings that take 23 hours to reach the nearest human ear. And it is doing all of this on a power budget smaller than a refrigerator light, with a computer that has less memory than the key fob in your pocket. The engineers at JPL, who manage the mission today, were not born when Voyager launched. Some of them learned about the spacecraft in school before they learned how to drive. They inherited a machine from a generation that is mostly gone, and they are keeping it alive with software patches sent across 25.8 billion kilometers of vacuum, hoping each command arrives intact, hoping the response comes back, hoping the fuel lines have not frozen overnight. Voyager 1 will reach 1 light day from Earth in November 2026. That means a command sent at the speed of light will take a full day to arrive. The response will take another full day to return. A 4-8-hour conversation with a machine that was built to last 5 years, still flying, still transmitting, still carrying the sound of rain and Bach and a baby crying into a place where none of those things have ever existed. The hum is still there, faint, persistent, narrowband, the interstellar medium vibrating at a frequency that corresponds to roughly 0.05 electrons per cubic centimeter. A whisper from the space between stars. And for now, one small machine with 2 instruments and a failing power supply is the only thing in the universe listening to it. We built it, we launched it, we are losing it, and when it goes silent, the void will be exactly as it was before we arrived, unmoved, unaware, full of a hum that nobody will hear. The interstellar medium will close around the spot where Voyager's signal used to be, and the plasma will keep vibrating at 3 kilohertz, and the turbulence will keep cascading, and the magnetic field will keep holding its unexplained orientation, and none of it will change because we stopped listening. The universe does not require an audience. We were the ones who needed to hear it, and for 49 years, one small machine gave us that. If you want to understand what the James Webb Space Telescope found hiding in the same darkness Voyager is flying through, and why some of it should not exist, according to our current physics, that video is on screen now. Subscribe so you do not miss what comes next.